So today we're going to slow things down a little bit again and do another lecture on the iPad. And what we're going to be doing is thinking about how to think recursively. And what I'm going to do is, by means of some examples, give you some advice about how to think about writing recursive functions in a language such as Haskell. So concretely, what I'm going to do is introduce you to a simple 7-step process for thinking about writing recursive functions, and I'm going to illustrate this by means of 3 examples. And the examples will get more sophisticated as we go on. The first one's almost trivially simple, just to kind of get into the process, and then we'll increase the sophistication in the second and third examples. If you happen to be reading along in the book, everything we're going to do today is covered in section 6.6. So to kick things off, I want to just think about 3 simple questions first of all, which are kind of really refresher type questions. So the first one is just a quick one. What actually are recursive functions? So if you're studying this course in Nottingham and I ask you what is a recursive function, all you write down for your 1 point in the exam is a recursive function is a function defined in terms of itself. So it's self-referential, very simple idea. Second simple question, refresher, is why are recursive functions useful? So one of the ways I like to think about this is that when you start off with functional programming, recursion perhaps seems a bit unnatural because maybe you're used to more imperative, kind of loop-based programming in languages like C and Java. But part of the point of learning a functional language like Haskell is once you get into it, you find that many, if not most, functions have a very simple and natural recursive definition. So another reason why recursive functions are useful is because in a language such as Haskell, fundamentally, recursion is ultimately the only way of doing any kind of looping or repetition. So if you want to program in a language like Haskell, you need to write recursive functions. And a last answer I'd give to this one here is if you write your functions recursively, then you get one of the mathematician's most powerful reasoning tools, which is induction, to reason about your programs as well. And as I've said before, we're not really going to cover reasoning in this course, but I do teach an advanced course in the 2nd year if you're interested in learning about that. So this brings me on to the final question here. Why are recursive functions difficult at first? So for me, I think it's really a different way of thinking. As I've just mentioned, if you're used to programming in an imperative language like C or Java, you get used to this kind of imperative, state-based, loop-based way of thinking. So it's a different way of thinking, so it takes you a little bit of time to get used to it. And I think there's a useful analogy here. If you can remember back to being a kid and learning to ride a bike. So when you're a kid and you see somebody else riding a bike, it looks really easy. And then you get on it and you fall off and you find that you need lots of practice to do it yourself, even though when you're watching somebody else do it, it looks really easy. So I think it's the same with writing recursive functions. If you see someone like me who's been doing this for many years, writing recursive functions, you think, well, that looks easy. Then you try and do it for yourself and you find out that you need a bit of practice to do it. So it's like riding a bike. It looks easy when someone else is doing it, but you need a lot of practice to be able to do it yourself. And for the Nottingham students, just a quick comment here, you can't learn to ride a bike the night before your cycling exam. So make sure you do keep up to date with learning how to write recursive functions. So what we're going to do now is introduce the idea of having a 7-stage process for writing recursive functions by looking at 3 example problems. So the first example problem we're going to look at is this one. What we have to do is define a function that calculates the sum of a list of numbers. And this is just the familiar sum function from the standard library. Probably many of you who've been following along with the course could already just write a recursive definition for this. But the point here is that I want to show you how to come at a recursive definition for this function in a very systematic way using a 7-stage process. So let's have a look at the stages. So what I've done on the slide here is I've written the numbers 1 to 7 down, and we're just going to fill in what the 7 stages are, and then we'll apply each of them one by one to this particular example. So the first step we're going to do is trivially simple, but there's a point I want to make here. We're going to give a name to the function which we are going to define. And again, sounds trivially simple, but in functional languages like Haskell, you tend to have very, very short names for functions and their arguments. If you're programming in a language like C or Java, the culture there is you tend to have quite long descriptive names for things. In Haskell, you tend to have very short names. So in this case, we're just simply going to call the function exactly what it's called in the standard library. We'll just call it sum. We don't call it sum of a list or sum numbers or something like that. We just have a very simple one-word name for the function. Okay, so that's the first step. And again, the point I wanted to mention is you try and be very concise when you're writing things in functional languages. So the next step now is we're going to write down the type of the function. So write down its type. And the idea here is that types really help you to define the function. Okay, so let's write down a type for this function. So it has type, and I'm going to say it takes a list of integers, and it's going to give me back a single integer. Okay, so I've not decided to be clever here at all. I could have done something fancy with numeric types and so on, but a good strategy when you're defining functions using this process, or just defining functions in general, is write down a simple type first of all, and then maybe you can reflect on it and simplify it or generalize it later on. And in this case, we'll find out that we can do exactly that. So the message here is we're having a simple type for now, and types really help you to define functions. So I've been writing Haskell for a long, long time. I always write down the type of a function before I proceed to actually thinking about how to define the function. So the next step then is we're going to enumerate the cases for the function. So we're going to enumerate the cases. So what does this actually mean? So this means writing down what I sometimes in the course have called the skeleton for the function. So each basic type has a number of standard ways that you can define functions over, or a number of standard patterns. So for example, if we look at the summation type, it's taking a list of integers as its parameter, and we know that there's two standard patterns for lists. You have either the empty list or non-empty list. And similarly, for any other kind of input type, there's standard patterns. If this was just taking a single integer as an input, you might try the skeleton 0 and n. If it was taking a boolean as an input, you might try just matching on false and true. Okay, so when you enumerate the cases, you look at the type of the argument or the arguments, and you try some standard cases. So we're going to write down the skeleton here, or enumerate the cases. So we could say what happens when you sum the empty list. And we'll do something later on for that. And what happens when you sum a non-empty list, x followed by x's. Okay, and note here, I'm not trying to fill in anything on the right-hand sides at the moment. I'm just thinking, what's the obvious skeleton or enumeration of cases? And again, we have a list of things here. So I match on the empty list, and I match on a non-empty list here. Okay, so that's the third process in the definition. An important point here is that you may need to refine these cases later on. It may not be the case that these default pattern matchings for the empty list and a non-empty list, these might not be the right ones to use for this particular function, but my advice here is you always start with the standard ones, and then you can refine these later on. And we'll see examples of that, this idea, when we come to some more sophisticated examples. So that's it with the third stage. The fourth step is we're going to define the simple cases for the function. So define the simple cases. Okay, so the simple cases often just turns out to be base cases for the recursive definition, but not always. So let's have a look at this particular example. And in this case, this is going to be our simple case. It's very easy to decide what we're going to do when we sum a list with nothing in it. And by definition, if you take the sum of 0 numbers or no numbers or the empty list of numbers, that's 0, because 0 is the unit of addition. And that simply means if you add 0 onto anything, it doesn't change it. Okay? So the right base case here, or the right simple case, is to simply return 0. The sum of the empty list is nothing. And again, comment here, the simple cases are often, but not always base cases. Okay, so that's the fourth step. So the next step now is we're going to list or think about the ingredients which we have left to define the other cases. So we're going to list what I would call the ingredients. So just like when you're making a recipe, you need to know what is available to you when you're trying to bake a cake, for example. And it's the same here. We're now trying to fill in the right-hand side here. And this is the tricky part. This is going to be the recursive case. But before we come to that, it's useful to think, what ingredients have I got available to kind of complete the definition here? So there's a few bits and pieces. So when we're trying to complete the right-hand side, the ingredients we've got available to us is we've got the function itself. Actually, let me highlight it up here. We've got the function itself because we can do recursion in a language like Haskell. We also have the two parameters. So on the right-hand side here, the variable x and the variable x's will be in scope. X will be the first thing in the non-empty input list, and x's will be everything else. So that's some ingredients as well. Also, what we could use on the right-hand side is we've got integer constants. Remember, we're trying to return an integer, so we could use some integer constants like 0 and 1 if we wanted. And again, because we're trying to return an integer, we could use some integer operators from the standard library. So things like addition, multiplication, and so on. So again, we're just reflecting on what we have available to us as ingredients to solve the more difficult case. So then we can go to step 6 in the process, which is define the other cases. And these are typically going to be, but not always, the recursive cases. Okay, so this is usually the tricky part. And in this case, actually, it's quite simple to know what to do. If you want to sum a non-empty list where x is the first thing and x's is everything else, all you're going to do is we can use the simple pattern of recursion, which we've been learning about, called primitive recursion. And we can do x plus sum of x's. Okay, so nice, easy one-line definition. Okay, so we've got a recursive decomposition here. We're summing a non-empty list by taking the first thing, recursively summing everything else, and then adding on these two numbers at the end. Okay, so this is the kind of the tricky part. It requires some experience, but again, some basic advice. Try the kind of simpler patterns of recursion first. So this is what's called primitive recursion here. So you might think, well, that's the end of the process. We've got a definition, but there's a really important final step now. And in some sense, this is the most important step. It's think about the result. What have we got? Think about the result. And there's two things you can do when you think about the result. You can look at something like this and think, can it be generalized? And in particular, can its type be generalized? And then also you can look at the definition and think, can the definition itself be simplified? And this is a really useful process of reflection. So let's think about the type first of all. If we think about the type here, we're taking a list of integers as an input and giving back a single integer. But if you look back to the problem description, we're talking about a list of numbers. And in fact, the definition here will work for integers, it will work for floats. In fact, it will work for any numeric type. Okay, so we can reflect on this now and think we don't need to make the function specific to integers. We could actually make it more general. So what I can do is I can get rid of that type here and I can generalize it and say for any numeric type A, we have the type list of A to single A. Okay, so here we're using the numeric class here, or the num class, which is inhabited by types which support standard numerical operations like addition and constants like 0. So the real type of the function, the part we're actually interested in, is this one here. We're taking a list of things and giving back a single thing, provided that the things are numeric. Okay? So if you type this definition into Haskell and you didn't have the type, and you asked the GHC system to calculate the type for you, this is what it would give. This is the most general type for this function. So we've managed to generalize the type. The last step here now is to look at the definition and think, can we simplify this definition? And in fact, we can, because this is the pattern of primitive recursion that we have seen in one of the recent classes. So primitive recursion says you process the empty list by giving back some value, you process a non-empty list by taking the first value, recursively processing the remaining values, and then you combine it with some operator. So we've got exactly the pattern of primitive recursion here, and as we've seen, this is captured by the fold-hour operator. So what I can do is get rid of this recursive definition, and I can redefine now sum to simply be fold-hour of plus and 0. Okay, and the idea we learned about last time is fold-hour captures the pattern of primitive recursion, and you tell it what to do in the recursive case, which is addition, and you tell it what to do in the base case, which is return 0, and it takes care of all the recursion for you. Okay, so this is the end of the process here. This is a nice simple one-line definition for the summation function as a fold, and it's got a nice general type now. So you might be thinking, well, this has all been really trivial. You could have written this straight off the bat. You don't need a 7-step process for this. But my experience with this is that when you're trying to learn to write recursive functions, having a kind of a helper thing for you, like this 7-step process, can be quite useful to you. And my advice is kind of, if you try and skip too many steps at first, it can kind of lead to frustration and confusion. So for our second example, we're going to look at a function which is a little bit more sophisticated than simply summing a list of numbers. And this will kind of illustrate some of the points about this 7-step process. So here's the problem we're going to solve for the second example. We need to define a function that drops a given number of elements from the start of a list. So for example, if you dropped 5 elements from the start of a list, it would remove the first 5 elements and give you back everything else. So this is a library function. We actually saw its definition in lecture 6 on recursion, but I'm going to show you how you can come at this definition, which is not immediately obvious, by following this simple 7-step process. So we'll start at the beginning with step 1, which is just name the function, and this is just a simple drop library function, so we use exactly the same name. So we'll call the function drop. Then the second step in our process is we're going to write down the type of the function. So you can kind of read it off from the problem description. You've got to drop a given number of elements from the start of a list. So you're going to take a number and you're going to take a list and you're going to get a list back. So what drop is going to do then is you give it a number. So let's say you give it an integer and you're going to take in a list of things and you're going to get back a list of things. So this is a very natural type for the drop function. It takes a number, like 5, takes a list of things, and it's going to remove that number of elements from the start of the list and give you back a list again. But already at this point, we've actually made 3 design decisions about the type, and it's important to be kind of recognizing what we're actually doing here. So we've made it into a curried function. It takes 2 parameters, one at a time, because we have the 2 function arrows here. It's also a polymorphic function because we're taking a list of A to a list of A. And also we decided the particular order of the arguments. We decided to take the number first and then the list rather than the other way around. And this is quite natural to do this because you want to say something like drop 5 from a list. Okay, but again, there's 3 design decisions here, and it's important to be aware of those kind of things when you're writing down the type of functions. So the third step now, if we look back to our little chart here, is enumerate the cases. Okay, so what does this mean in this case? Well, we have an integer here, and there's 2 standard cases for an integer argument. It's 0 and n. That's the kind of default cases that you try. But we also this time around have a second parameter. We have a list, and the default cases for lists are the empty list and non-empty lists. So we have 2 cases for the integer and we have 2 cases for the list. So we're going to have 4 cases overall. So we're going to write down a skeleton with 4 equations. So write down the parts here. So I could drop 0 elements from a list with nothing in it, and then I'll get back something. I could drop 0 elements from a non-empty list, x followed by x's, and I get back something. And then I could also drop n elements from a non-empty list, or from an empty list rather, and I get something, or I could drop n elements from a non-empty list and I get something. So again, there's two possible things that the first parameter could be. It could either be 0 or n. And then there's two possible things that the second parameter could be. It could either be the empty list or it could be a non-empty list. So there's two things for the first parameter, two cases for the second parameter. So we have all four possibilities. Okay, so we're not trying to be clever at this point and think, oh, could some of these cases be combined or something like that. We just write down the four cases and we'll think about in the last step, can we actually simplify or generalize this definition a little bit. So the next step in the process is number 4, define the simple cases. So it may not be immediately clear what the simple cases are, so we'll just go down them one at a time and think, is it obvious what to do? If it is, then we will just write down the definition or figure out what the right thing to do is. So if we look at the first case here, if we're dropping 0 elements from a list with nothing in it, well, this is quite easy to decide what to do. All we're going to do then is give back a list with nothing in it. Okay, that's a very easy case. If we want to, in the second case, if we want to remove 0 elements or drop 0 elements from the start of a non-empty list, again, there's really nothing to do there. We're not actually going to remove any elements, so we can simply return the input list again. So x colon x's. Then we come to the third case, and here we have a choice to make. So we know at this point that n is not going to be 0. So let's imagine it's going to be a positive number now. Suppose the integers are only positive here. So we're trying to drop a positive number of elements from a list which has nothing in it. So maybe we're trying to drop 5 elements from the empty list. Well, we've got a design decision to make here, because if we're trying to drop 5 elements from a list with nothing in it, well, what do? Well, one possibility would be just to crash or throw an exception. What the Haskell designers decided to do is just to return the empty list here. Okay, so it's just a little fallback case here. If you try and drop 5 elements from a list with nothing in it, it doesn't crash, it doesn't raise an exception, it just gives back the empty list. And then you come down to the final case here and you think, well, is this a simple case? If I'm trying to drop a positive number of elements from a non-empty list, well, maybe I need to think a bit about this one. So I'll come back to this one later. Okay, so now we go to our next step in the process, which was to list or think about the ingredients. So we want to try and define the right-hand side for the last case here. So what do we have available to us? Well, we can use the fact we're trying to define a recursive function. So we could use the drop function itself. This time around, we have 3 variables we could use. We could use the integer n, the first value in the list x, and the remaining list x's. And then, because if we look at the type of the function, it's to do with integers and lists. So we could use anything in the standard library to do with numbers or lists, so constants and operators as well. And again, sometimes it's easy to forget what you can use, so it's kind of useful to reflect and think, what have I got available to me to try and build the right-hand side? So step 6 now is define the other cases. So let's have a think about this. So what does it mean, or how do we drop a positive number of elements from a non-empty list? So for example, imagine we were trying to drop 5 elements from this list here. Well, how could we do this? Well, we could decompose that by simply, let me write this down and then explain it. Oops, wrong thing. I could simply drop n-1 elements from the remainder of the list. So what does this mean in practice? So if I'm trying to drop 5 numbers from a non-empty list, how could I do that? Well, I could drop 4 numbers from the remainder of the list. So this would make the integer smaller, and eventually it would get down to one of the base cases, and then this would stop. Okay, so again, this is maybe the point where you need to kind of stare at this a little bit and maybe kind of turn the handle with an example or two and think, how could I actually come up with this definition for myself? Okay, so now we've actually got a working definition. Then we can think about the result. We can have a think about it, think, can we generalize it and can we simplify it? So the generalization typically happens with the type. So you might think, well, I could generalize this to any kind of integer type. I mean, this doesn't really work if you give it a float as an argument, maybe any integral type or something like that. Actually, GHC doesn't do this, and I asked the GHC designers why they didn't have a numeric, a more general type in here, and they said it was for efficiency reasons. And actually, I don't really buy that answer. I think you should just make the type as general as it can possibly be, and let the compiler worry about making it efficient. So really, I think this should be a more general type that's got something to do with any integer types, of which there's more than one. Then we can think, how could we simplify the definition? And actually, there's a few bits and pieces which we could do here. So if we look at the first two cases, here we have this, dropping 0 elements from an empty list and dropping 0 elements from a non-empty list. Notice that in both cases, we simply don't change the input list. Okay, so what we could do here is combine these two cases into one, because if you're dropping 0 elements from any old list, you just get back the list unchanged. Okay, so what I could do is, let me get rid of one of these, get rid of that one, and then I could simply write here, we're going to get any old list X's coming in, and we'll get the same list back. Okay, so just to neaten things up, let me just drag this up here. So all I've done here is combine the first two cases into one. And then we can look, well, can I simplify things a bit further? And actually, yes, we can. If we note here, we don't use the variable n on the right-hand side. We just have the empty list. So I could replace that n here by a wildcard character, because we don't care what it actually is. And if we look in the last one, also, we're not using the variable x. It doesn't appear on the right-hand side. So we could get rid of the variable x. So I could get rid of that one and fill in a little underscore here as well. Okay, so this is our final definition, which we've obtained by following the simple 7-step process. And this is exactly the definition which you will find for the drop function in the standard library. And again, this is one of these examples where if somebody shows you the definition, it's kind of easy enough to figure out what it's actually doing. But if I asked you to write this definition, it's probably, when you haven't got too much experience with Haskell, quite difficult to do. And this is why this 7-step process is actually quite useful from time to time. So here's the problem we're going to be looking at for our final example. What we have to do is define a function that removes the last element from a non-empty list. Well, what does this mean? Well, for example, if it's given the list 1, 2, 3, 3 is the last element, so it should remove that and give you back the list 1 and 2. Okay, so we've got to define a function that removes the last element from a non-empty list. So we just follow our simple 7-step process. So the first step again is to give the function a name, and I'm going to call it exactly what it's called in the standard library, which is init, which stands for initial segment. Then the second step is to write down its type, and there's an interesting observation to make here. So basically what this function is doing is it's taking a list of things as its input. It's going to be completely polymorphic, and it's giving a list of things as its output. So this is the type you will find for this function in the standard library. But there's a point to note here. It says in the problem description that it should remove the last element from a non-empty list, but this type here is any old list. This could be an empty list or a non-empty list. Okay, so actually the Haskell type system is not quite powerful enough to express part of the problem description that this function should only work for non-empty lists, because when I see this type here, this could be the empty list. There's nothing to stop me calling the function with that. And just as a little aside here, if you wanted to look at programming languages where you can make much more precise statements about types, then maybe you want to have a look at dependently typed languages such as Agda and Idris, which are kind of the successors of things such as Haskell. But for now, we're just writing a Haskell program, so our function takes a list of A's as an input and gives back a list of A's as its output. So then we go on to the third step, which was to enumerate the cases. And in this case, there's only one case to consider because the function is only got to be defined for non-empty lists. So whereas for the list parameter here, there is normally two cases, the empty list and the non-empty list case. In the problem description, we see that we don't need to consider empty lists at all. So we'll just write down one case then, this time around. We'll say init of a non-empty list, where x is the first thing, x's is everything else, and then we'll decide what to do with that later on. So again, there's no case for the empty list this time because that's forbidden by the problem description. So now we can think about what actually are the simple cases. And actually this time around, defining the simple cases is the key step to actually making this function actually work. So let me write down what the simple case actually is, and then we'll have a kind of comment about it. So I'm going to have two guards here. I'm going to say otherwise down here. I'm going to say null x's up here. So what does this mean? Well, I've got two guards, so I'm making a choice between doing two things. So in the first case, I'm saying, is the remainder of the list empty? And null is a little library function that takes a list as an input and returns true if it's empty. So all I'm doing here is checking, is this list here actually empty? So why is this going to actually be a simple case? Well, if the list x's is empty, that means x is the only thing which is in the list, and that means x is the last element. Okay, so if I reach the case where the tail of the list is empty, so null of x's, that tells me I can remove the x because that's the last thing in the list, and I'll simply get back the empty list. Okay, so this first equation here is just a fancy way of saying in Haskell, if you have a list that's only got one thing in it, x, then you've already found the last element and you just remove it. Okay, so again, this is the key step this time to observe that actually the case when this list here is actually empty is actually a simple case. Then the next step is to list the ingredients to help us to define this part. So what do we have this time? Well, we have the init function, we have the two parameters x and x's, and we have any library functions and constants to do with lists. So then that brings us on to the next step, which is to define this particular case. And again, we just need to kind of stare at this a little bit and think, what's the right thing to do? Well, in this case, we know that x is the first thing, and because we're in the otherwise case down here, we know that this list here is non-empty. So that's already telling us that x is not the last thing in the list, because the tail of the list, x's, is not empty. So in this case, what we can do is we know we've not yet found the last element, so we can keep the x, and then we can just recursively take the initial segment of what's left. Okay, so this is the way to recursively break down the problem in this particular case. So this is now a working definition, and you might want to think, well, how can I understand this? And again, you could just turn the handle with it, apply it to a simple example, such as init of the list 1, 2, 3, and turn the handle, just unwind the recursion a couple of times, and you'll find that you get the list 1, 2. So the 3, which is the last element, gets removed from the list. So this then brings us to the last step in the process, which is often the most interesting one and where things kind of simplify and get more general. So we could think, what could we do first of all? So could we generalize the type first? So we look at the type. Well, there's not an awful lot we could do with that. It's basically as general as it can be. It's a polymorphic function. It's taking a list and giving us a list. Not an awful lot we can do here. So we'll look at the definition and think, could we simplify this in some way? So the first observation I want to make is we could actually replace the use of the guards here. So we have two guards, we're checking if the tail of the list is empty, and then if it's not empty, we could actually just replace this by pattern matching. So let me rub the definition out and show you how you could do the same thing, but using pattern matching rather than guards. So the first case here, I could say, if I've got a list with one thing sitting in it, then the initial segment of that, or removing the last element, is just the empty list. So that corresponds to the first equation which we've just rubbed out. And then the second equation is exactly what we just had, the bit I've rubbed out. if you have any other non-empty list, so you know that this list has got at least 2 things in it, because if it's got 1 thing in it, that's already been trapped by this case here. So if you've got a list with at least 2 things in, what you're going to do is you keep the first thing, and then you recursively call the init function on the remaining list. So this is exactly the same definition as what we had using guards, but I think it's a bit cleaner or easier to understand using pattern matching, because here I'm directly expressing what happens when I have a list with 1 thing in it and what happens when I have a list with at least 2 things in it. Okay, so we're nearly finished with this definition now. Something you should always do is look and see, are there any variables which are not being used on the right hand side? So I can see one of them here. Here the variable x sitting in the list on its own. It does not appear on the right hand side here, so I could eliminate it. So I'll get rid of the x and I can put a little underscore, which is a wildcard pattern in here. And again, if you look in the standard library on the web page for the module, this is exactly the definition which you will find for the init function. And again, if I just showed you this definition, it's fairly easy to understand and kind of track through an example for yourself. But what I've shown you is a simple process by which you can actually invent or discover definitions like this for yourself. So just to wrap things up today, I'd like to just make a few concluding remarks. I mean, I've shown you a process here, but don't think of this as being some kind of law that you have to do. It's really a guide for you. You don't have to use it, but it's useful sometimes when you're learning how to write recursive functions or when you get stuck. And what you'll find is that with experience, you can skip steps or actually forget them completely. And once you've been doing Haskell for a while, I still think though that there's 3 of these steps which are really, really crucial. And this is something which I do myself all the time, even though I've been doing Haskell for 25 or 30 years or so. So for me, the 3 of the most important steps are writing down the type before I actually define the function, because the type really helps me to structure my definition. Enumerating the cases, so just looking at the parameters, thinking if it's a list, I can have an empty list and a non-empty list case. If it's a number, I can have a 0 and an n case. Enumerate the cases, don't try and be clever, and then you can try and fill in the function definition. And then the third of the steps, which I think is really useful, is the final one, which is generalizing and simplifying. And typically, you might generalize the type, and you might try and simplify the definition by maybe combining some of the parts, maybe using folds or higher order functions or something like that, maybe using wildcard patterns and so on. Okay, so that's it for today. It's just a kind of quick lesson on kind of how to think recursively, and I will see you again as usual next time.